So welcome to our second video on model-based reinforcement learning. In this video, we will be talking about background planning. So what do we actually want to do in background planning or environment data augmentation? So the basic idea in background planning is actually to mix real and model-generated experience data and to apply traditional model-free methods such as Q-learning or policy gradients to the problem at hand. So in a sense, what we actually do in background planning, we want to assist other maybe model-free reinforcement learning agents with building a model jointly with training the agent to actually help to get better solutions. So a very early but very intuitive and nice idea of doing this is DynaQ. So the general idea of DynaQ is to use collected data to learn a transition and reward model, as we already have introduced it in the last video, and then actually to train a traditional reinforcement learning algorithm, which could be, for instance, Q-learning, using both environment data, so the real experience, and data generated from the learned model, so from simulated experience. So in a sense, the model helps us to offer a larger augmented training dataset for the RL agent. So we see a little sketch diagram here. So from the real experience that we get from the environment, we train using direct reinforcement learning updates, our policy or value functions. But at the same time, we also use this real experience data to learn a model of the environment. And from this model, we can actually simulate experience that we can also use to update our policies. So what you see on the right side is the pseudocode of DynaQ, which actually reminds you a lot about what you actually know from traditional Q-learning. So lines A to D are actually like vanilla Q-learning as we have introduced it in the early videos of the lecture, where we actually have in D our traditional Q-learning update. So line D is just working on the sample that we receive from the environment, and we just do our Q update in our simple bootstrapping manner as we already did it before. What's different now is line E and line F. So in line E, we actually take the environment sample to actually train our model, our predictive model on that data. And what we also do in each step of the environment, while we actually take a real environment sample to actually train our Q function, we do in F we repeat over n times, and we actually randomly select a previously observed state from our model. We randomly sample an action that we previously has taken in S, and we run our model on SA to get actually the reward and the successor state that we can expect from this state and action combination. And using this simulated experience, we can actually do the same Q-learning update that we did in the beginning, while we do it here only on the data that is simulated through the experience. So in other words, actually, in the last line, we use the model to create imaginary transitions from the states and perform the same Q-learning update on these as we have did it on the real environment samples. So we can also take this one step further and run and actually execute model-based policy optimization. So the idea is very similar to what we have seen in DynaQ. However, in model-based policy optimization, we really train our policy only on synthetic model rollouts. So the general idea is actually the same as in DynaQ, because it relies actually on a predictive model of the environment. So a transition model that is parameterized by theta, could be a neural network, for instance, and it returns a successor state and a reward given a state and action pair. So this is actually what also DynaQ is doing. What we then do is we apply traditional policy gradient methods only on the synthetic model rollouts. And we take actions in the real environment, of course. So let's go through the pseudocode shortly. So we start with a randomly initialized policy pi phi, a predictive model p theta, and an environment dataset d environment and d model, which are actually holding the different datasets that we sample either from the environment or from our model. And then we iterate over certain epochs where we actually train a model P theta on the environment data via maximum likelihood. So this is just a supervised regression problem, and we can just apply traditional methods of machine learning that are well understood. What we then over E steps do is we take an action in the environment according to pi phi, and we add the sample that we get to the environment, because we actually did an action in the environment and we get a sample from the environment. We can actually put it in the environment data set, and from there we actually do, or not from there, but we actually do now M model rollouts. So what we do is actually we sample we take a uniformly sampled state ST from our environment data set, and what we from there do is we perform a k-step model rollout starting from ST using our policy pi phi. So actually we use our trained model and we start running it, and all the data we gather using our policy, and all data we get, we just append this data to our data set of the model data set. And what we then do is actually we take G gradient steps. And what we simply do is we take the data that we observe from our model and we just run a policy gradient update using the data that we just got through the interaction with our environment model. So in a sense, while we train our policy entirely on the synthetic data, we every once in a while take actions in the real world, and we actually our model is actually going better and better over time as we receive more environment samples, and we train our policy simply on the predictive model that we actually train from the environment samples. Okay. One thing to do on top of this, which is very usual in practice, so these two approaches that we have seen are very commonly used in practice, and what you also see a lot in practice is actually the topic around domain randomization and simulation to reality transfer. So usually what you're doing is if you are having a simulator or a model available, which is in many cases you could actually assume that you have a model or a simulator available, you can usually train your RL agent there. And however, the simulation will always be different compared to the real system. So if you just train an algorithm or a reinforcement learning algorithm using this model on a simulator, and then you transfer this model to the environment, you will actually see that in many cases it just doesn't work. So there is cases actually where it does work. However, in many robotic use cases, the mismatch between the simulator and the environment is just too large, and you just overfit it too much on the simulator. What's a great solution in this idea to actually improve your reinforcement learning agent that has actually been working with the model is actually to learn on a distribution of similar environments. So what you can actually do is you can actually modify or change physical parameters. So if you remember, for instance, the card pole example that came across a lot of times, you can maybe change the mass of the card a little bit, or the length of the pole, and you can change physics to actually generate a distribution of different environments, and you can actually let your RL agent train on this distribution of environments. So this helps a lot to actually increase robustness of your reinforcement learning agent, and there is enough hope that you have then trained a policy that you can actually more easily transfer to the real world. So this, in a sense, is also model-based RL, where you actually train an agent and you actually assist it with different models of the simulator, of the environment, or the predictive model, however you would call it. And in this way, you can assume that the real system that your model is actually working on, or your agent is actually interacting with, is actually nothing else than another variation for your policy. So actually, you can expect your model to work better in such cases. While this seems super simplistic, it works remarkably in practice. However, there is a lot of effort that you actually have to deal with in the randomization of the environments and tuning of the hyperparameters of your RL agents to actually work properly on that scenario. Okay, so we have seen actually how to augment environment data and perform simulation to assist reinforcement learning agents in their task of learning a policy or a value function. However, there's also, I mean, we assisted the RL agent. The question is now, how can we also do it? And what we also could do is, what we didn't now explicitly do is, we could also allow to train our agent and our model together in an end-to-end way. So the success of what you've seen in deep learning method comes from the end-to-end approach, that you actually work on raw image data, for instance, and you extract the features together with their classifier to actually form a pipeline and train the pipeline end-to-end, and this is much more efficient in practice. And the idea is, how could you actually come up with an end-to-end framework that works, that actually trains a policy together with a transition model in an end-to-end way. So this is actually what we will introduce a little bit on this slide, and which is also what we will be revisiting in later videos of this series. So to sum it up again, we train a model and a policy jointly in an end-to-end fashion. In other words, we want to do what successfully worked in other domains such as computer vision and speech recognition. And just go back to our original goal. So our goal in reinforcement learning is that we want to maximize the reward of a parametric policy. The policy is parameterized by parameters theta, and we want to maximize the discounted future reward, actually. And we have some side constraints on this, because we actually select actions AT according to policy P theta, given ST, and our next state is actually the output of a transition model, TSTAT. And the question is, why couldn't we just use this end-to-end with a parametric model and just apply gradient descent on the policy gradient? Yeah, so I mean, the question is how to calculate the gradient of J in this case. And while this conceptually is very simple and clean, remember reinforce, where we actually also derived something like this. We have a high variance and we require a stochastic policy in this case. And maybe we can, while this is not working like that, you cannot plug this in like one-to-one on this scenario, we can take all the ideas we actually did when we introduced reinforcement learning, when we introduced Monte Carlo policy gradient. And the question is now, how can we actually do this here? Yeah, we can do more, because actually we can assume to have smooth models, and smooth models also offer derivatives. So we have, for instance, a model, a transition model Fs, which could be a neural network, and it could also be differentiable. And it can be a function that just returns st plus 1 given st and at. And we might also have a reward model that returns RT given ST and AT. And if our models are smooth and offer derivatives, we can just derive them. And we can ask questions like, how do small changes in the actions affect the next state? Or how do small changes in the states affect the next rewards? And as we can actually answer these questions, or put it differently, if we assume models that let us answer such questions, we can use like end-to-end differentiation. We can do an end-to-end differentiation of our objective function via backpropagation. You can just estimate all these gradients and partial derivatives in a sense using the chain rule, or you do it automatically via autodiff in PyTorch. So actually, how could you do backprop on such a model? So what you see in here is we have, if you like build up a computation graph of what's happening if we do the model rollouts and if we do our policy. This is something that is actually happening if we run our policy, if we train our policy, and if we also make forward passes through our model. So actually our function f theta SA is actually parameterized by theta, and we have also the policy in here. Could be the same set of parameters that actually has been shared, and this is actually what we see. So we actually take a state S and we put it in our function, and we get it returns an action. We put it in our function, and we get a reward out of it. And what we actually want to do is we want to maximize our objective function, which is this one. And what we could actually do is we can just run a baseline policy, just initial version of pi, which could be a random policy, and we collect data samples d as a as prime. From there, we learn a dynamics model f phi as a by minimizing a mean squared error on this one. And what we can do is we can just backpropagate through the model to actually optimize our policy. So this is the basic idea. So we can just go through and we get the rewards, and we have our model which is a differentiable model. And using this model, we can actually backpropagate the gradient all through our network to actually optimize our policy. However, remember there's a distribution mismatch between real data and data that we currently already, between real data and between the real world and the data we already collected. And what you have also seen in previous examples, such as DynIQ or model-based policy optimization, is the idea to run this in combination with real data. So actually, what you would then come up with is it's a little bit a better algorithm, or a version 2 of it. Maybe instead of just running a baseline policy, learn the dynamics model and then backpropagating through the model to actually optimize our parameters. We just then also run our policy in the real world, and we actually receive new tuples that we can actually add to our data set, with which we can actually come up with a better dynamics model that actually better captures what's happening in the real world. And we can then run through this in an iteration and actually learn both the model and the policy in an end-to-end fashion, both at the same time. Okay, so what's the basic idea behind it? So backpropagating through the model to optimize the policy. First, we approximate transitions and rewards with differentiable models, actually to allow to take a gradient through it. And then we calculate the policy gradient via backpropagation through time, which is also well understood and well known from recurrent neural networks training, which is something that sounds or looked already very similar to you, maybe if you have gotten to know RNNs from other lecture formats. Yeah, so actually there is some pros. So we have a long-term credit assignment. We can actually see what's going on, and we can actually assign the gradients correctly. We have differentiable transitions and reward models, which is good for sample efficiency, so we can increase a lot. And the principles behind backpropagation through time, they are well understood. So we actually know them from recurrent neural network training for quite some time. And it is a deterministic thing, and there's no variance involved in here. However, there's also a few downsides. So while backpropagation through time is well known for the training of RNNs, we also know that for training long RNNs, so RNNs with large sequence sizes, we actually see problems of vanishing and exploding gradients, which is in a sense a problem in the optimization concerned or actually prone to poor conditioning. So our models are poor conditioned, or problems are poorly conditioned. And while we actually solve this in RNNs by using gates, and like in LSTMs, for instance, where we have a forget gate and things like this, we cannot just add such gates to our dynamics, because actually the dynamics are chosen by nature, and there's not really a sense of having a long-term memory of such things that happened in the praxis. And of course, it's prone to local minima. As we train this end-to-end, there is a high chance to actually end up in a local minima. So this is it for background planning. So in the next video, we will talk about, in the next 2 videos, we will actually talk about online planning, which goes a lot more into the direction of real-time decision-making and real-time planning, when an agent actually uses a model in real time to actually, during deployment of the system, to make a plan of what's happening and what actions to select in the next time steps.